Hey everyone, good morning. I would like to welcome you to this garden conference and I'd like to thank the organizers for inviting me. Today, we are going to discuss about agentic AI for material design with atomgpt.org. My name is Kamal Chaudhary. I'm an assistant professor at Johns Hopkins University with material science and engineering, electrical and computer engineering, and data science and AI Institute affiliations. I'm also a research associate at National Institute of Standards and Technology in Maryland, where I served as a staff scientist for 10 years before joining Johns Hopkins. This is the outline for my talk. So first, we'll discuss about an overview of agentic AI. Then we'll go to the ChatGPT Material Explorer, then move on to the atomgpt.org API or AGAPI, and then we'll also discuss about benchmarking and hackathon about agentic AI. So let's start with the overview of agentic AI. Now, before we go in AI, and this is a buzzword almost everywhere in each field of science, can we take a pause and think about what intelligence really is? Now, if we look into some of the papers, such as Universal Intelligence, the Book of Why, the Measure of Intelligence, the Cambridge Handbook of Intelligence, one thing is quite clear. The definition of intelligence itself is not very clear, right? You broadly, intelligence can be considered as an ability to adapt, to generalize, the ability to reason, and there are some measures of intelligence, such as Stanford Binet, IQ test, Turing test. In neuroscience, specifically, if you do EEG analysis, gamma waves in brains are often associated with intelligence. However, it's very clear that the definition of intelligence remains still under argument. Now, when you talk about artificial intelligence, the idea is to mimic human brain, but artificial intelligence can be considered as an umbrella term. Within AI or artificial intelligence, there's a machine learning term that deals with data, like 500 or more. In deep learning deals with much larger data sets. Generative AI is a part of deep learning which generates content such as text, image. Agentic AI can take action on behalf. So one of the review articles specifically from material science were written in 2022, and you can see this paper has been cited about 1,000 times. So feel free to check out if you're interested to learn about deep learning or AI in material science with this article. So now, why do we need agentic AI? So these are some of the current limitations. Material discovery is quite slow, expensive, fragmented. Traditional AI can predict properties but cannot act on their behalf. Specific scientific workflows require multi-step reasoning, tool chaining, iterative decision making. The question is, can AI behave like a junior scientist? LLMs or generative AI models, which we'll discuss about, often are associated with huge hallucinations, so provide incorrect results with high confidence, or psychophancy, where LLMs is over positive and try to praise you instead of critiquing you. There are many models which are commercial, so even they are can be cheap, they are still require a credit card to work with these models, and they're black boxes. Outputs are non-reproducible, so if you ask a question today, few minutes or few hours from now, you may not get completely different answers. So science depends on reproducibility. So this leads to a challenge. LLMs are often trained, or AI models are often trained on vast amount of internet data, not specifically for physics, chemistry, math, biology data. So how can we solve these issues? We can either teach the model. So what I call teaching is connecting the brain or LLMs with scientific databases, such as with RAG tool calling MCP A2A, which we'll briefly discuss about. Or you can train them where you can actually train the model on a custom dataset using LoRa or PEFT. Now, the future is agentic. There have been several works and several documents from Google and OpenAI to learn about agentic AIs, especially this particular document, the practical guide to building agents, was super useful to me. Now let's briefly discuss about what is predictive AI, generative AI, and agentic AI. So in predictive AI, we are quite familiar. It comes with input and output. It's quite static tasks. So for example, predicting properties with CGCNN, align, or other models, formation energy, forces, energies, prediction, powder excel diffraction, classification, VAE diffusion model. These all lie under the area of predictive AI. Generative AI can produce content such as text, image, data, can be passive. Agentic AI takes it to the next level where you have both brain, generative AI, and also hands, which can take autonomous actions, can be goal-directed behavior, solves problem using tools and planning, can call APIs, search databases, and run calculation or experiments. Now let's start with a very simple example of this LLMs or generative AI and why do we need agentic AI. This is a famous example called strawberry test. Suppose we go to the website atomgpt.org, sign in and so on, and select few models. So we went there, we selected GPT OSS from OpenAI model, Llama model from Meta, and Gemma model from Google and asked the question, how many are in strawberry? Now you can see the first model gives you three, which is correct. The Llama model give you two, while Gemma model give you three as well. Now, no judgment on company and itself. I just want to point out these catastrophic failures in AI models are often accompanied with little to no explainability, which remains a critical issue in trusting AI model or trusting AI data. And that's why benchmarking remains very important. Now, how can we fix this problem? We can make an API to count R in the word, like strawberry. How to do that? Suppose we have written a small Python code on the right-hand side. You can see count R, which takes a string and count R in it. Now, if you count R in strawberry, it will give you 3. Now, we can take this Python code, serve using Fast API, and host in AWS. That becomes your API now. An API to count R in a strawberry. And now you can expose it to LLM model, and then it will be able to interact with this API and give response instead of giving its own response. And that's how we can solve the issue of R in strawberry. One of the way how we can solve the R in strawberry problem. Now, was a very simple example. Think about materials. This is really hard. And we're going to discuss about why agentic AI for material science is a hard problem. For instance, in material science, we deal with heterogeneous tools like ab initio DFT modeling, molecular dynamics, experimental and many other experimental technique and databases. We have combinatorial challenges, nearly infinite possible materials. Reproducibility, so it is reasoned and shown based on this paper that only 0.5 to 30% papers are reproducible. While if you see the mainstream AI, you can, for instance, um, take a MNIST or ImageNet data set and classify digits. Super straightforward. But can we do that for instance making 99.9999% aluminum oxide? No, we can't do that. So that reproducibility remains a challenge. Non-standardized outputs. So are your data, is your data compatible with some schema, like Open API schema? Running long-range experiment and computation can make the overall agentic process slow. So we need faster tools and hopefully decently accurate tools. As I said, there are many models which require a credit card information to interact with their API. So especially if you're a student and so on, it becomes tricky. And over the years, the cost really builds up. So we need open models, open LLM models. Let's show you an example of this Iron Man where uh, Iron Man clip, we're trying to design an arc reactor with several lanthanides and other elements. And what we are primarily doing is structure property performance relationship. You can see even in the movies, it remains so tricky and challenging, let alone solving material design in real life tasks. Luckily, because of this MGI in 2011 and US CHIPS Act have been proposed and used to accelerate material design, and now there is a proposition of Genesis mission coming soon. Now, one of the infrastructure that came out from MGI plus chips is the JARVIS infrastructure. Of course, the name you can see is inspired from the movie Iron Man. It's available at the website jarvis.nis.gov. And now it has been also been integrated in the website atomgpt.org, which we'll discuss. The idea is to use density functional theory, quantum mechanical method, force field machine learning, and other tools to design or optimize new materials. In Jarvis DFT, we have a diverse amount of data. So, for instance, we have about 80,000 materials, unlike many other databases which just have something like a PB exchange correlation. We have an improved van der Waal obviate functional. Most of the database you might know severely underestimates electronic band gap, which makes them unreliable. So we take effort to use meta GGAs to improve those band gap predictions, spin orbit coupling interaction. We converge K-point and cutoff for each materials automatically. We have a workflow for that. Of course, we had to make some choices. Nothing is perfect, but we have to make reasonable choices to be a part of a NIST website. So we making this convergence um, renders the calculation about 5 to 10 times low, but at the end, we can get reliable results. We also convert energy and forces. We have data for elastic tensors, piezoelectric tensor, dielectric tensors, electric field gradient, superconducting transition temperatures, 2D materials, Raman spectra, Seebeck coefficient, solar cell efficiency, spin orbit coupling, spillage for topological materials, 1 year tight binding dataset, STM images, surface defect, and interface properties for up to 1.4 trillion interfaces, which is crazy, I mean, in my opinion. Um, so the Jarvis infrastructure is used worldwide. Although it started in 2017, we have published over 50 articles, over 6,000 citations, 200,000 users worldwide. We have about 2 million data and software downloads, and we have some of the really nice comments from the communities. For instance, there are many different theoretical levels on which you can approach to the field. Jarvis is unusual in that it spans more levels than other databases. You can find downloaded about 2.4 million times, and I was told this is like highest fixture downloads. If you're not fixture, this is a data repository. So now let's discuss about we discuss about Jarvis. Now let's discuss about ChatGPT Material Explorer. So it was inspired from this post. Just it came up as a feed on my phone from Google News. For instance, introducing GPTs in 2023, November 2023. And the idea is you can make your custom chat GPT, which at that time was really crazy, really amazing. Um, so if you go to chatgpt.com/gpts, or you can click on explore GPTs, you'll have a platform where you can specify a name, a description, a few instruction, and few other custom instruction that will let ChatGPT talk to other external tools and reliable resources and work on a particular way that you want. And that was the motivation and the idea behind making ChatGPT Materials Explorer. This still remains available, and we did not solve everything with ChatGPT, but we have only 3 or 4 main tasks. For example, integrating with Jarvis DFT and search for a particular material. So instead of making it up or hallucinating about what are the materials in Jarvis, it will talk to the database and then give you reasonable response. In addition to database searches, we added graph neural network models, archive search in ChatGPT, and based on some of my suggestions from my colleagues, I actually submit to a journal, which got a lot of attention. So we compared with some other agentic models like GPT-4o, ChemCrow, and ChatGPT Material Explorer seems quite reasonable, especially when they are interacting with external database and tool such as Jarvis and Align and so on. We'll discuss about. So this made a lot of news. Johns Hopkins made a huge article about this. A lot of um, well-known community members made YouTube videos about this. So this is nice. These are some of the existing efforts in agentic AI for materials that I am personally aware of, and there can be many more. So, for instance, Gabe Gomez Group from Carnegie Mellon, Cam Crow from Andrew White Group, from Al Aspuruguzik Elegante, from Marcus Buehler Group, this particular paper on alloy design, LAMP, SciTool agent, ChatGPT Material Explorer, and of course, AGAPI agents that we'll discuss about today. One thing to note, most of the agents that we discussed use commercial API except AGAPI, so you don't need to put your credit card information to use these agentic features. Now, that leads us to the atomgpt.org API. If you go to the atomgpt.org, it comes with this website. You can sign in with your email or continue with Google or GitHub. While ChatGPT Material Explorer was based on commercial models such as ChatGPT 5 or 4.0, AtomGPT heavily relies on open source model. There are currently about 8 plus open source LLMs hosted for free, no cost. It also comes with tools and web apps such as searching for materials databases, property prediction tools, protein structure design, X-ray diffraction tool, literature search. None of your data is stored or used for training. You can store your data or export your data if you like, but this is not our intentions like these major companies to sell or use your data in unethical way or any way possible. It's also compatible with function calling, tool causing, MCP, and other features. Currently, we have about 3,000 users worldwide, and the AGAPI GitHub page is available on AtomGPT Lab/AGAPI, so you can check out for more details. Another thing I want to point out, um, there's a common consensus to share our data script on GitHub docs, but I think in the age of agentic AI, that's not enough. We need to make our work, our best of our work, available as an API. And that's doing great service to the community. And this is one of the reason the name AGAPI was chosen, which is a Greek word which means unconditional love. So let's discuss about key design principles of AGAPI. So we discuss AI agents have brain, LLMs, API, hands, and orchestration. Suppose we have to design this or we have this prompt. Study the effect of nitrogen substitution in silicon carbide and so on, right? We have to discuss. This used to be a undergrad project, for instance, a few years ago. So you search for a material, you optimize the structure, dope the system or substitute the elements, predict band structure, and then do literature search. Now, this is all done on a prompt level, and that's the beauty of agentic AI. You can have this input, and then select a LLM, which we call brain. So you have multiple LLM, and one of the default one is GPT OSS 20 billion parameters. Tools or hands, such as JARVIS, DFT, Align, and other tools. And of course, plan, execute, and summarize actions. Now we discuss about LLMs. We have already discussed about it. Now let's talk about the tools or API calls. So if you go to the API tools or go to atomgpt.org/docs, you'll get to know several tools that you can use for your own workflow directly. And these are open API specification compatible. So for instance, we can go here and you can see we can have the API from the atomgpt.org website. Here we are searching formula, but we can also perform several other tasks. So here we are searching for aluminum oxide, put our API key, execute. Now your data is available in a particular format that you can adapt in your workflow. And there are many other uh, keys, API endpoints such as align FF, protein folding, SLACONET band structure, archive API, and so on. So let's start with a very simple example. We discussed about we are still discussing about AGAPI infrastructure. So let's start with how to install and how to use it. One simple example is this pip install AGPI, how you can get the package. And then from the website, you can go to the settings and get your keys here. And now you can interact with atomgpt.org website on on scripting language or use your Jupyter notebook or Colab notebook. So you can have a AGAPI key, use this AGAPI agent, and ask a super simple question: what's the capital of US? Now here, this is just interacting and getting response from LLM. Now, what we can do is use tools equals to true and ask a question, find all aluminum oxide materials in JARVIS DFT, for instance. And instead of making it up uh, IDs and compounds with LLMs like GPT OSS, it will talk to external databases and then give you the response, which will not be hallucinated. And this is using a library called OpenAI agents. Another example is for instance, how many superconductor materials are there in JARVIS? Now, this is a question that can be asked in different way. And the agent, the LLM, should be able to figure out itself which tool to talk and give the response. And this is based on this paper, Designing High-T Superconductors, which was one of the first papers on high throughput, large-scale uh, superconductor discovery paper. So now it's available as API and Agentic API, for instance. We can also do materials comparison. So for example, you want to compare silicon, silicon carbide, silicon germanium, and then you can compare band gap and other properties. Of course, not the underestimated property, but high accurate band gap properties and so on. And it will also provide you analysis of those values. You can interact with agents using graph neural network model prediction. So suppose a material is specified with a particular ID, currently is primarily linked with JARVIS. So you can ask for align-based property prediction. Align is a model that was proposed a few years ago. It has been cited about 600 times or more, which showed how using many body features at bond angles can improve the task performance. And using now this model, you can use this agentic feature to predict properties like band gap, superconducting transition temperatures, shear modulus, bulk modulus, and so on. You can also use the web app. So on atomgpt.org/align, just hit a predict properties and look at all these properties. So you can use this both as an agentic way or a conventional web app way. You can also have machine learning force field integrated with it. So you can have a postcard file and ask the agent, optimize the structure with AlignFF, and it'll give you the optimized structure. This was one of the first universal force field model, which came in around 2022. Another model, which is Slaconet, is a tight binding model for the entire periodic table, has been integrated in an agentic way, and that can be used, for instance, semiconductor design. Now, this is a very complex workflow compared to the other workflow that we saw in the previous examples, where this just one prompt. Here, we are asking multiple things. So, for instance, find all the gallium nitride materials, get the postcard, which is the atomic structure for lowest formation energy material, make a supercell, substitute the element, get the X-ray diffraction pattern, report the peaks, optimize the structure with AlignFF, predict the properties, calculate band structure, and then create a summary table. Now, this all is done in an agentic way, and at the end, we get this nice, beautiful band structure in your chatbot within few seconds. So, which is quite promising for semiconductor design. Now, of course, you can also use Slack-o-net. Just put your atomic structure file and calculate band structure, and within a few seconds, it can predict band structure with high accuracy. You can also design heterostructure, which are quite important for device design. So, for example, you want to make a device with gallium nitride and aluminum nitride with 001. So you can just chat about it. Like, I want a gallium nitride structure with most stable, aluminum nitride, which is most stable, and make an interface with it. And it's based on a project called Intermat, which was used for predicting band offset in semiconductors. And now you can design with your chatbot. You can also do not just computational, but experimental analysis and experimental acceleration. So this is based on a paper called DiffractGPT framework. So for instance, you can discuss about find all the materials, like gallium nitride materials, get me XRD peaks, report 10 strongest peaks, or I have the strongest peak. Uh, what is the atomic structure of that material? So that's the idea behind DiffractGPT, which is a GPT-based model. This is a fine-tuned model, not agentic model, but it can be also made available in an API. Very interestingly, this model has been downloaded about 125,000 in just 1 month. Just to put in perspective, DeepSeek model is download 200,000 in a month. So compared to that, we can clearly see a material-specific model like DiffractGPT is getting traction at the level of mainstream media, which is quite interesting to see. Now, of course, you can interact with DiffractGPT in an API way or in a web app. So, and also we can consider DiffractGPT model as an alpha forward for material science and engineering. So here, for instance, let me show an example of Lab 6, which is standard reference material. And you give the 2 theta intensity and ask to generate atomic structure using both phase matching and DiffractGPT way. So you can get the phase matching based atomic structure and of course, DiffractGPT, which is a LLM-based atomic structure. Now, the most interesting part, now suppose I don't know what elements are there in my material, and suppose I suspect it's nitrogen there. Now, if I run this app again, you'll see because this material does not exist in database, there is no way to compare it. However, DiffractGPT will generate the material for you and compare. So it is a new feature that has been added because of the DiffractGPT model. It's also available, as I said, in an API format. We can also use AtomGPT API to search for materials and search literature at the same time. So suppose here in this instance, we are seeing how ChatGPT and other LLMs model can hallucinate and make fake citations. Wouldn't it be nice to add it to agentic in an agentic way features such as archive and crossref to reduce this hallucination? In fact, in recent NeurIPS, it was found that hallucinated citations found in papers from NeurIPS, the prestigious AI conference. So this is a major challenge, and one of the way we can solve it, especially for materials, for instance, if you search for bismuth telluride in this particular app, of you'll get from papers from archive which are authentic, and also get comparison from JARVIS TFT database, so you can do one-to-one comparison. So now how do you benchmark this agentic AI? And that leads to the last section of this talk. This is very difficult. So we can, as we mentioned, agents have LLMs, so we can benchmark LLMs. We have APIs, so we can benchmark APIs. But together we can also benchmark for well-known materials. For instance, we took the band gaps, electronic band gaps, bulk modulus, superconducting transition temperature, solar cell efficiency, and dielectric constants um, from Jarvis leaderboard benchmarking platform, experimental values, and did this really interesting test where we had predictions from the base GPT OSS model and the agentic models, so with tools and without tools. What we found was super interesting. We found that the tool augmentation is not universally beneficial. Its effectiveness depends critically on three factors: whether your database quality is and coverage for target property is consistent, especially for well-known materials. The superconducting transition temperature is available in literature. The GPT OSS was able to predict this quite accurately. While if we are connecting with DFT databases, there's a huge approximation in while predicting the TC with DFT, and that leads to overall lower accuracy for this agentic feature. And of course, as I said, whether the material is well known, well documented or not. And except bulk modulus, we found that for literally for other, it's very comparable. Just the GPT OSS model is prediction is comparable. And this is interesting, but this may not be the case for unknown materials. And there we might need physics-based model to predict properties. We organized a hackathon called Agentic AI for Science Hackathon at Johns Hopkins and virtually in November. And it was well attended. Over 120 participants, undergrad, grad, postdocs, and other attendees attended it. We have a GitHub page for this. You can find all the details about it. We'll be organizing one in 2026. So stay tuned for that. Once you sign up for atomgp.org, you'll get these updates. This is a collaboration chart that was made from a program I wrote and linking my Google Scholar. So the basic idea is I'm open to collaboration. If you have ideas, let us know. I'd like to thank the team member. This is my group website. So overall, I want to point out the future is agentic. Let's share our work as an API. And now I would like to, before I open the floor for question, these are some of the contact websites, some of the web links. The AGAPI agents paper is an archive and under peer review process. Hopefully it gets through soon. ChatGPT Material Explorer is published. We can also connect in social media. I also have a YouTube channel called Dr. Kamal Chaudhary. So please feel free to check that out if you're interested in data-driven material design. With that, I would like to thank you for time and attention and happy to answer any question if you have.